Hello, my name is Greg Herington, and today I'd like to present on the topic of Nash equilibrium. And before I dive into it, I want to apologize in advance for the background noise. Unfortunately, the headset I was using to test this recording software broke on me. So, we'll go ahead and get started. And in order to get to Nash equilibrium, first we must talk about games. Now, in a branch of mathematics and economics known as game theory, we can classify games into two categories: sequential move games, such as chess and tic-tac-toe, and then there are simultaneous move games where we do not have full information because we do not know what the other players are going to do. Simultaneous move games include rock, paper, scissors, and if you're a Big Bang Theory fan like I am, rock, paper, scissors, lizard, Spock. Now, it's fairly trivial to find the best solutions to sequential move games like tic-tac-toe, as is explained by this comic at xkcd.com. We see that we can map out the solutions to our problem, and here is a map for X. So if we know what our opponent's going to play, we can make our decision based on the winning strategy. And here's the one for O. Now, because chess is so much more complex than tic-tac-toe, the best strategies can be mapped out if you had enough computing power, which no one has near enough for. But to move back over to simultaneous move games, which we're more interested in for the purpose of this video, we didn't have a way to map out the best strategies to use until Nash gave us the Nash equilibrium. Many years after discovering the Nash equilibrium, Nash was awarded the Nobel Prize in Economics in 1994, a prize which he shared with two other economists. One useful way to use Nash equilibrium can be seen in this example here, where on the top we are a small firm deciding whether or not to enter into an existing market where a large company already has most of the market share. So our options are: we can enter or stay out of that market, and the big firm, the incumbent firm, can either wage a price war or not wage a price war. As we'll see, it's hard to solve this using an algorithm, but it's quite easy to do by hand. So we can decide whether to enter or not to enter based on what our competitor does and the consequences of a price war or lack thereof. So the table you just saw is called a payoff table, and in that table you list the payoffs for yourself and your opponents. Now, maybe by now you're wondering if Nash equilibrium help us find best strategies for playing simultaneous move games. Then how do we find them? Well, I will show you how to solve for the Nash equilibrium using the problem known as the prisoner's dilemma, which is the gateway example for understanding Nash equilibriums. As you can see on this screen, the prisoner's dilemma example says that two friends are suspected of burglary because they've been found with stolen goods. So they are taken into custody and interrogated separately. Now, there's not enough evidence to convict them of that crime since nobody saw the crime happen. But since they found them with possession of the stolen goods, they can charge them with that. Now, they have two choices. Each friend can either lie or confess to the burglary. So the payoff table is shown there at the bottom, lists the jail sentence in years. So what this payoff table shows is that if both prisoners lie and they don't admit to it, then they will only spend 1 year in prison for possession of stolen goods. And if they both confess to it, they will get 8 years in jail. Now this other square and this square are interesting because they represent a plea bargain offered by the police to each prisoner. If prisoner 1 lies but his friend confesses that both of them committed the burglary, then his buddy will walk free and he will be put in jail for 10 years. This is prisoner 1 we're talking about, 10 years. And the same is true the other way. If prisoner 2 lies but his friend confesses, then prisoner 2 will spend 10 years in prison and prisoner 1 will have all charges dropped. So what the Nash equilibrium will tell us is what is likely to happen given these circumstances. And the process to find the Nash equilibrium is as follows. We assume the role of the first player, which here is prisoner 1, and we think from his vantage point, and we will assume that prisoner 2 is going to confess. So would it be better for us to also confess or to lie? Since 8 years in prison is better than 10 years in prison, we'll want to confess. So we'll underline this first 8 here. Now, if we assume that our friend is going to lie, then since we are the first coordinate, it would be better for us to confess because we would get out of jail free. So we'll underline this 0. So now we switch roles to prisoner 2 and look and see what our options are and payoffs from this vantage point. So we will assume that our friend prisoner 1 confesses. Well, since we are prisoner 2, we have the second payoff. And if prisoner 1 confesses, then we should also confess, because 8 years is better than 10 years. And if our friend lies, then it would be better for us to confess, since we would get the get out of jail free card here. So we'll underline this one, and as we'll see that our underlined show us the Nash equilibrium, which is any box that has all numbers underlined. So this is what is likely to happen. Both prisoners will confess and spend 8 years in prison. And the reason for this is because each prisoner wants to minimize their time, but they're also risk averse. They do not want to risk an extra 2 years in prison, even though they could get off on a lighter sentence, because they're not sure what their friend is going to do, since they are separated and cannot collude. Now that we've done one example, I find it helpful when learning new concepts to try a few different examples to help me remember the process. So why don't we tweak this problem a little bit, and let's say that both of these prisoners are in a gang. So their payoffs are going to be a little different. The rule of their gang is if anybody rats out another member of the gang, then they'll die. So their payoff, if they confess, we'll say it's negative infinity. So why don't we take a look at that example? Okay, here is our modified payoff table. As you can see, if anyone confesses, then their outcome is much worse than it was before. So what we do in this process, let me move this down here, we follow the same process and we assume the role of prisoner 1, and just like Schrodinger, we'll look at what's going to happen if prisoner 2 confesses and if prisoner 2 lies. So let's start with, if we think our friend is going to rat us out, then our payoff is better if we keep our mouth shut, and if our friend lies, since we're this first prisoner, this first coordinate of this pair, it would be better for us to only have 1 year in prison than to suffer the consequences of ratting somebody out. Now we swap over to prisoner 2's role, and we see that if our friend confesses, it is better for us not to confess but to lie. So as prisoner 2, we don't say a word and we take the 10 years in prison. Now if our friend also lies and we confess, then we'd be worse off than if we also lied. So what this shows us is that under these new circumstances, the outcome is likely to be that both prisoners will lie and get off on a light sentence. So what Nash's framework does is provide us with a good way to look at incentives and analyze the payoffs. Now there are many uses for Nash equilibrium in games and in problems. A few problems that come to mind is the manager-employee problem, which essentially is how frequently should a manager check on his or her employees to make sure that they are not slacking, but the manager also wants to not waste his or her time. Another example would be price setting between companies. Should I raise or lower or maintain my prices? Well, it turns out it depends on what you think your competitor is going to do and the consequences of that. Another place where Nash equilibrium can be used are in election strategies, but the one I want to come back to is the one I mentioned earlier in this video, which in our example is we are a small firm and we're deciding whether or not to enter into a market where a large incumbent firm has most of the market share, and the risk associated with entering is that the large firm could wage a price war. So why don't we look at that payoff table? Here in the top payoff table, let the small firm, our firm, be represented by this enter, don't enter section, and we'll switch it up a little bit and we'll use coordinate X, or this first coordinate, for the small firm, and the incumbent firm, who's our large competitor, will represent down here, can either wage a price war or they can leave things how they are. So we follow the same process to find the Nash equilibrium, and what these payoffs here represent are each firm's net income for that year. So our firm's net income would be negative $1 million and our competitors would be $8 million. Let's assume that the large firm is a publicly traded company So they want the best net income they have, just as we do. So following that same process, we as firm, the small firm, assume that they are going to wage a price war. So should we enter or not enter? Well, it looks like we should not enter. Pardon me, it looks like we should enter because 0 is better than negative 1 million. Now, if we assume that they will not wage a price war and let us enter, then we should enter since our net income will be 2 million as opposed to 0. Now, if we look at this from the incumbent firm's perspective, we will assume that the small firm is going to enter, therefore we should not wage a price war because it hurts our net income so much. So we want to underline 18 million because 18 million is better than 8 million. And if we assume that they are not going to enter, then there's no reason to wage a price war because it's just us. So we'll underline this. And as you can see down here at the bottom, our Nash equilibrium shows that the big firm will not wage a price war. Therefore, we should enter so that we can get 2 million of net income. I'd like to point out in that previous example that lower right square should not have a red underlining. My apologies for that. I want to thank you for taking the time to watch this video. If you would like to find more information on Nash equilibriums, there is a plethora of information on YouTube and on the web. Thanks.